Ladies and gentlemen, welcome to the ICE-Technical meeting Tseung Kwan or Tulam Tin Rock Tunnel Design and Construction. This event is brought to you by the Institution of Civil Engineers. My name is James. I'm from ICE Student Chapter BINUS University, and it's a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be opening remarks by the chairman of ICE-Jakarta Local Association, Phil Lutmancy. After that, the event will be guided by Phil Lutmancy as our moderator to start the presentation of Ivan Haryono. The event will then continue with a Q&A session. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can ask your questions for the speaker by pressing raise hand feature located at the bottom of the screen. The question should be in English. And you can raise your question after the presentation of the speaker. Now, I would like to invite the chairman of ICE-Jakarta Local Association, Phil Lutmancy, to give his opening remarks and also guide this webinar as our moderator. Now, please welcome our moderator, Phil Lutmancy. To Phil Lutmancy, the time is yours.
Okay, thank you, James, and good evening, everyone, and welcome to our webinar put together by the ICE-Jakarta Local Association. Tonight's presentation is on the Tseung Kwan to Lam Tin Rock Tunnel. And it's a great personal pleasure for me to reconnect and to welcome Ivan. He's a colleague and friend. Before I came to live in Jakarta, I was based in Hong Kong, and it was on this project that we worked together for what was 3 or 4 years of my life. It's a very special project to me personally, because I had the fortunate position to lead the Golder team through the tender design, the whole design and construction. Thankfully, I had people like Ivan in the team leading the design side of things, but yeah, one of those very special projects that you don't often get in your careers, and this was a good one. So I'll hand over to Ivan. He's controlling the slides tonight from Hong Kong, and just ask him to bring up the first one, and I'll just talk about the first 2 slides before I hand over to Ivan. So the presentation tonight is put together based on a couple of presentations that we've done previously in the for conferences in the US and Malaysia. It's a design and construction project, and it's a very large rock tunnel in Hong Kong. So just have a look at the next one, Ivan, please.
Just hang a sec.
That's okay. There we go. Just to let you know, in case you don't know where Hong Kong is, south coast of China, and just showing you where it is relative to Jakarta down in the bottom of the screen there. So next one. So, yep, so just this oblique view shows the project layout. So those of you do know Hong Kong or don't know Hong Kong, you can see the old alignment of the airport just on the left of the harbour there. It's the new airport is no longer there, but that's where it used to be. Hong Kong Island is on the left of the screen. And our project, Lam Tin portal, is there round to the Tseung Kwan portal on the other side. The tunnel length was about just over 2 kilometres. The whole project was about 4 or 5 kilometres, but actual just over 2 kilometres of rock tunnel. through that section. So, yep, it was a sizable project. Coming off the Tseung Kwan portal, you go into the Cross Bay link, which is now a major road connection off where Ivan's just indicating there. And then from the other side, the Lam Tin portal, there is now a new tunnel which goes on from Lam Tin towards where the old airport is. And then you can also go from the Lam Tin portal across onto the Eastern Harbour crossing to get over to Hong Kong Island. So Hong Kong is generally well known for its rail, its MTR system, but this is a road tunnel. Intention was to relieve congestion in this area, build it in anticipation of population growth, and just generally improve connectivity for motorists in this area. So yeah, a big job. So I think that's enough from me. I will welcome and look forward to listening to Ivan. Thanks.
Thank you, Phil. So some overview here. As we mentioned, the project is 2.2 kilometer long road tunnel, and the project cost probably a few years ago was about $1.2 billion US. It was design and build contract, and the tunnels and the caverns were excavated using drill and blast method in jointed granite and volcanic tuff. And on average, the span of the tunnel is 16 meter. The height is about 11 meter. However, there are some caverns, actually, if you see on the right-hand side, we have one bifurcation cavern, which we will talk about later. And this is another twin caverns at the Tseung Kwan portal, and you can see the size here is 25 times 31 meter, 25 meter wide and 31 meter high. And you can see the little excavator there, just to show the relative size of the whole cavern here. The bifurcation cavern is quite spatial because the span is quite large. It's 34 meter, and the height is 14 meter. Now, what we faced back there was we had geological faults at intervals, and some locations we need to excavate beneath the existing metro tunnels and foundation of the Paris buildings. Now, Golder was the contractor's designer for the tunnels. So our scope was to compile geological information and make 3D geological modeling, and also characterize the rock mass condition. And we also need to predict the hydrogeological condition and also groundwater inflow of the from the rock mass. And to allow the contractors to build the tunnel, then we need to design temporary support for the rock, and also cross passages and tunnels and caverns. And we also need to work together with tunnel team to assess the constructability and also sequencing of the excavation. And because we need to pass sensitive receivers such as MTR, or metro tunnels and buildings, we need to do impact assessment, modeling, ground movement prediction to show to authorities and existing stakeholders that the tunnel will not cause any adverse effect. And we also help the contractors to develop a geological and geotechnical risk register for the tunnel and site formation works. Also, we provided a statutory site supervision during excavation, and we also carried out rock face mapping. The contractors were Leighton and China State Joint Venture, so that both are actually two big contractors in Hong Kong. Now, about the works, the design of the permanent tunnel support actually was carried out by government consultant, or we call it the engineer here. If you see, the permanent tunnel is the green color there, right? Now, upon the award of the contract, the JV or the contractors would need to carry out excavation and construct the permanent tunnel support based on the engineer's specification. our task means Golder and the JV is to excavate and to install temporary tunnel support, including shotcrete and bolts, and to design the excavation sequence such that the team can get or excavate safely. And then I need to mention that there are some interesting issues during the construction, including like controlling groundwater inflow, as well as some excavation beneath the MTR tunnels and also the faults area. Now let's go to the construction challenges in more detail. Sorry. Now, the job was quite interesting because yes, it was very challenging, and you can see the span is pretty large. And as of today, the bifurcation cavern is the largest cavern in Hong Kong, and the excavation was carried out in different overburden situations from 10 meters below surface to 200 meters below surface. And we would need to design various tunnel support in different rock mass conditions, including 8 different faults with various degrees of weathering and fracture intensity. So at that time, geological modeling was really critical for advanced understanding as to what we should anticipate. And because of the variety in ground conditions, we should carefully consider excavation sequence in certain high-risk areas. If you see here, we have MTR crossing. I will discuss this a bit later. And we can see there are some high-rise buildings here. And the bifurcation is located here. It's literally in the middle of nowhere, but we have a water reservoir here. Now, the other challenge is the logistic and progress of the works rely on one single access, means that any problem or bottleneck will actually make the excavation progress difficult, and it may risk the program of the project as well. Now, apart from the excavation itself, there are some issues with, in fact, the work or controlling the blasting during excavation beneath the MTR crossing, and I will talk about it a bit later as well. Now let's go to some overview on the rock support design. So if you see the question there, why we need support for rock? Well, rock is strong. Typically, we will consider as strong as concrete or even stronger. And if you realize about concrete column or beam, they can stand up without any support. And that's true if rock doesn't have, if concrete doesn't have fractures. In fact, in rock mass, most of the problem, especially near surface area, the problem is we have joints, and therefore we will have some potential instability because of the rock wedges. Now, most of the joints are governed by jointing caused by the tectonic movement in the earth crust. And if you see on the left-hand side, this is a clear picture from Dr. Effort Hook, which shows instabilities around underground openings in deep mines. And you can see most of the failures there. There are some small rock wedges, and in fact, they are falling down from the crown of the tunnel. So if we think about safety, the unstable wedges can cause fatalities if left unsupported. Therefore, we should install temporary support or permanent support even earlier to just make sure that everything is stable and safe.
Ivan, it's Phil here. Sorry, just to interrupt. How about you share your video so we can see you?
All right, sure, no problem. I suppose you can see me now. Yeah, so just to explain a bit more about the rock support design process. So to ensure there's no instability during excavation for design, we start with ground characterization and modeling. And then after that, we will use typically empirical method, for example, Q system or RMR, both provide some sort of early design concept, but then we need to clarify or verify further with more assessment. For example, we probably need to carry out wedge stability analysis or even numerical modeling. Now, after that, we need to consider the excavation sequence of the tunnel because there are some stress distribution and it might be causing some problems to the adjacent tunnels, for example. Now, after we carry out those steps, typically we need to design like instrumentation and monitoring system to ensure that our design is appropriate. We need to design the instrumentation monitoring system such that we can verify. So our role as a designer is not stopping in the design process only, but also we need to verify and evaluate our design later on. And the other important part here is mapping on site for verification. So typically we will have boreholes. If you see the right hand side here, this is a photogrammetry resource of one of the portal, and these lines are boreholes with different ground materials, but sometimes the relative size of the boreholes is not as large as a tunnel, so often we don't have enough information. So rock mass mapping or rock face mapping is necessary to ensure that our assumption is correct. Now let's go to, this is the empirical design approach. I present a Q system approach here. This approach is typically adopted in Scandinavian countries, and in fact, all the data are coming from Scandinavian countries. And in Hong Kong, because the rock mass condition is quite similar to Norway or probably Sweden, therefore Hong Kong engineers typically use this method for designing temporary support, even permanent support for rock. If you see the chart here, these are all the design tools. It's a bit complicated, but you can see there are Q numbers or Q values here. Q values essentially is representation of rock mass condition. So the smaller the number, the weaker the rock, and the larger the number, the stronger or like more massive rocks. Now we can assess also the span or the height of the opening, and combining our rock mass condition and also the dimension, then we can come up with certain spacing for rock bolts and also certain thickness for shotcrete. Now in Q values, there are different considerations to derive it. First one is block size or joint spacing, and the second one is joint surface condition, and the third one is instance stress condition, and sometimes we need to consider water as well. So this is, well, it looks a bit complicated, but in fact, they are pretty much quite simple to do. Now, sometimes we use Q values to come up with some numerical input for finite element analysis. There are some limitations, and I'll go through it later. So this is the next step that we did for design. The first one, we will carry out wedge stability analysis based on joint input that we had. This is the CAVERN, actually, the large CAVERN we had, and you see there's brown color here. It's in fact a predicted wedge there, and you see many spikes there. Those are the design rock bolts. So we can assess the capacity of the rock bolts against the wedge size or height or volume, and we can get a prediction of factor of safety. Then we can try to like modify the support system such as that we can satisfy the factor of safety. On the right hand side, this is another exercise or assessment that we did. This is in fact a hybrid finite element model. We use joints there. In fact, we call it discrete fracture networks here. This is 2D model, and we incorporate the tunnel support and in fact the sequence, which I don't show it here. And then we can come up with some sort of ground movement prediction, as well as mobilize actual forces of the bolts or even the shockwave. Now from here, then we can conclude some sort of design for the tunnel later on. So I mentioned about our role. It's not stopping in the detailed design only. So we need to be involved in the site investigation during the excavation, because it's a must for us to verify and evaluate our design. And then when we get instrumentation and monitoring data, we typically will like back analyze or even probably redesign if necessary, so as to ensure that the excavation is safe. So the most important thing we need to remember here, this whole process, regardless whether it's geotechnical engineering or rock engineering or structural engineering, I think closing the loop is very important. Now we are going to the drill and blast tunnel excavation cycle. So it's a bit complicated. Typically before excavation, we will carry out probing or grouting as necessary. Probing is needed because we want to drill holes ahead of the excavation phase, so we can understand what is the potential ground condition ahead of us. And then if there's any groundwater flowing from the probe hole, then we will carry out grouting in advance. We do it that way because we want to control groundwater inflow before we excavate further. I need to remind that the tunnels here are mostly drained. So in fact, we allow water to flow to the opening. And it's in rock engineering is a cost-effective solution, in fact, because if we design as undrained tunnel, typically we will need to install very thick shotcrete or even cast in situ concrete, can be 500 millimeter or even 1 meter, just to sustain groundwater pressure. But the idea is here is to control groundwater inflow such that we can achieve a cost-effective solution for the tunnel excavation. And after we probe, we carry out the probing and grouting, then we will drill the blast holes, and typically we will need about 4 to 5 hours. And then after we drill our blast holes, we will we call it charging. Essentially, it's inserting the explosive emulsion. Because the face area is quite large, sometimes it can be up to 300 square meter. Therefore, it takes a bit of time, 2 to 3 hours. And after that, the foreman or the shot firer need to start the evacuation procedure before we carry out blasting. So all staff workers on site need to basically get out of the tunnel, and they need to go to master point, and the shot fire need to ensure that no one is inside the tunnel. And after the situation is declared safe, the shot fire will detonate the explosive. The detonation itself is pretty quick. It's probably less than 50 minutes. I put it 50 minutes here. In fact, it can be just 1 minute. And then after blasting, the shot fire need to get in again to the tunnel, and no one else can go into the tunnel. The shot fire needs to check whether there's any like misfire during the blasting. If there's any problem, then he needs to clear up the problem before other workers or staff getting back to the tunnel. And just before people are back to the works, the shot fire needs to ventilate the tunnel so the dust and the dirt can be cleared up before people go back, because it's quite dangerous and it's not safe for breathing. And after that, it's marking out time. So trucks will come in, and then they will carry out the mark out. They will take the rock out and deliver it somewhere. And there will be some equipment to scale back the loose rock wedges, for example, because sometimes if we leave the rock wedges as is, and in fact they are loose, then it might be dangerous for workers. And in fact, there are some incidents, probably not in this tunnel, but in other tunnels, there are some incidents, people working under the rock face, and some, rock blocks probably just as large as our head falls down, and then it will hit. Can be, it can be dangerous. After scaling, then engineers will come in. The first one is the surveyor. They will carry out survey. They will measure the tunnel perimeters, and then they will compare later with the design excavation profile. And then after that, another team will come in to install temporary support, including shotgun and bolts. And after that, the whole loop starts again. So it's quite a long story, and these are the pictures. I hope you can get some context here. You can see this is a drilling of the blast holes, and this is a charging, and you can see those cables will be connected to detonator later on. And this is the pictures during blasting. Of course, no one is there. The JV put a little camera just to record it, and then after that, it's marking time. You can see the trucks there bringing out the excavated rocks. And temporary support installation, the first one is installing shotgrid here. You can see the sprayer, and it needs to be uniform and smooth, and needs to be controlled as well. And after shotgridding is finished, we will continue with installing rock bolts here. You can see some notes there. Those are the plates of the rock bolts, and it's a little small here, but this is the steel bolts we use there. So now we are going to the interesting stuff, excavation beneath active metal tunnels. I'm sure, well, many of you are familiar with the left pictures here. This is Jakarta in the morning. It's very crowded, traffic jam everywhere. And I just want to show the comparison with Hong Kong here. People don't take car, and people rely a lot on MTR. And you can see this is one of the major stations in Hong Kong. This is Central Station. It's very crowded, very packed. And of course, this picture is taken before COVID period. During COVID, you can just imagine the same crowd with masks. Comparison between Hong Kong MTR and Jakarta, you can see left side is Jakarta MRT system. I think Jakarta MRT is Jakarta Mass Rapid Transit System, while in Hong Kong we call it MTR, Mass Transit Railway System. I believe we have one line. I think we are trying to expand a bit more. And in Hong Kong, the system is pretty major. We have about, if I remember correctly, it's 11 lines, and mostly they're undergrounds. Yeah, it's quite expensive, and it's also connected to the border to mainland China. So just a bit context, our tunnel is somewhere around here. Now, this is the picture of Lam Tin Portal where we had the crossing beneath the active metal tunnels. And this picture is taken back in 2017. It's still tidy. Now this is pretty messy. I can show you the latest update later on. So this will be a big interchange with viaducts, bridges, and it will be connected to the tunnel here. Now we have one edit or small tunnel here just to start the excavation of the tunnel while waiting for the site formation works to be carried out. And on the right-hand side here, you can see a little building here. This is the MTR tunnel portals. So this is the railway, and actually there are more than 2 tunnels later on. I can show you. Those tunnels and lines are in fact above our tunnels. And this is the 3D model of the situation. And this brown color shows the final site formation level of the portal. And we need to excavate from this level down to here, and then there will be 2 tunnels. And these 2 tunnels are actually for Tseung Kwan tin tunnels. The span here is about 18 meters. And you can see the red tunnels there, they belong to MTR tunnels. Now on the right hand side is another 3D view, just a bit different from the first one on the left, just to get a clear picture how it looks like. Now the challenge here is the tunnel, our tunnels, Tseung Kwan tin tunnel, is located with limited separation below the active MTR tunnels. From our crown level to the inlet level of the MTR tunnels, the separation is between, I think, 9 to 10 meters. It's quite challenging because if you remember the excavation cycle, the first one we need to do is to drill probe holes and grouting if necessary. In fact, this area is also in fault, so there might be some grouting necessary. And when we drill probe hole and grouting, there might be a risk of intruding the MTR tunnels, and it might damage the tunnel, and it will cause disaster basically for the JV and also the MTR. And blasting is a bit difficult as well because MTR has stringent requirement for vibration with limited separation here. The blasting works were really controlled, and I can tell that for the rest of the tunnels, we typically operate 24 hours. So there will be 2 cycles of blast, but in this tunnel or in this area, we can only do it 1 time, and it's only daytime. It requires close communication with MTR Operation Center. So I still remember during the blasting period, then tunnel team need to call the MTR operating center. They need to literally tell, I'm going to blast now, and is it safe? Is the train is going to pass or not? And typically the window is only 2 minutes. So if the JV miss 2 minutes window, then they need to delay the blasting probably to the next day. So in terms of program, it's quite like expensive. Now, I mentioned that the span of the tunnels here is 18 meters. It's quite challenging to excavate in terms of blasting, vibration, and also controlling ground movement. Especially we have fault area here. I will show you the relative location of the fault a bit later. Before going to the fault, I just want to highlight the stringent requirement from government. I also want to highlight that MTR tunnels are protected by law here, or ordinance. So if you see the requirement here, these are all taken by from the ordinance. The induced maximum movement of the tunnels by any works adjacent to the tunnels is only 20 millimeters. The maximum differential settlement is 1 in 1,000, and the vibration is less than 25 millimeters per second. In terms of movement and vibration is quite critical because we really need to control our sequence and also temporary support. Now, if you remember the separation thing we mentioned earlier, so here we say there's no bullet shall penetrate within 3 meter distance in any plane from existing tunnel. So 3D modeling was a key back then. What I mean 3D modeling here is 3D geometry modeling, because we need to predict where is our crown, where is MTR tunnel invert. So we need to predict where the bolts will come through. And further than that, approval from MTR operator is required. So we need to submit everything, our design, our method statement to MTR, and then they need to agree in writing that we can carry out the works. Otherwise, we cannot carry out the work, and it will cause further delay. Another thing to consider that if there's any exceedance in the requirement here, then MTR has the right to stop the works. Again, it will cost money and it will just compromise the program. Just a quick overview here. We've seen the MTR tunnels, and the blue blocks here represent the inferred fault of the in the area. And on the right hand side, you can see the plan view of the Tseung Kwan tunnel here, and also the MTR tunnels. Now, for design, basically we need to convince stakeholders, not just the engineer or government, but also we need to convince MTR operator. There were a lot of meetings, and yeah, a lot of discussion about what to do and what's the best way to move forward with the tunnel excavation. And eventually, we worked together with the tunnel team and also the blasting designer, and we come up with a design that we allow the JV to excavate 1 meter. We call it pool length. Essentially, it's the excavation length. There are 2 reasons: is to control the ground movement and also to control the vibration. So apart from that, we also support the rock with quite robust system. It's 150 millimeter shotcrete and 1.5 meter bolts spacing. And to predict all the movement and vibration, and we need to carry out modeling. So we carry out 3D finite element modeling, and also we design comprehensive instrumentation and monitoring plan, including automatic monitoring system for movement and vibration. Eventually, rock mass mapping is necessary to confirm whether our prediction is correct or not. Here you can see the 3D element modeling prediction for the tunnel movement. And on the right hand side here, we can see a plan view of the monitoring arrays for the MTR tunnels. So the survey team from the JV literally went into the tunnel and installed these prisms, and then they lay down the cables, and they measure the movement and the vibration automatically. And then they can extract the data from somewhere else. Now, in terms of movement, I'm talking here about, sorry, this scale is a bit small, but essentially all the movement is below 1 millimeter. So during excavation, it was safe, it was stable, and we managed to get through all the hurdles. And it was a bit slow compared to the other portion of the tunnels, but we managed to get it done safely. Another interesting thing is the bifurcation cavern. So I mentioned earlier, this is the largest cavern in Hong Kong to date. This is some comparison. In Hong Kong, we had previously built cavern. We have Island West Refuse Transfer Station with 28 meter span, 12 meter height, and Admiralty Station with 25 meter span and 16 meter height. Now for our Tseung Kwan tunnel bifurcation caverns, we have 34 meter span and 14 meter height. And this is the picture of the excavation of the caverns. I will explain this a bit more. Now, why we have such a large cavern? Now, the left side here shows a 3D model of the bifurcation cavern. We have 1 tunnel and 2nd tunnel. They meet together and they will merge into where we call it bifurcation area here. And the design from the engineer for permanent tunnel lining is like a M-shaped tunnel like this. So from a road engineering perspective and from tunneling perspective as well, this shape is quite difficult to build. We can build it probably, but it will take a very long time. So we need to come up with some solution for the JV, because if you remember, the JV relies a lot on single access to the the other end of the tunnel. So any delay in this area will compromise the program. Now, in terms of rock mass condition, it's strong rock, jointed, however, and there's a potential fault area there, but we see that the fault is probably minor. However, excavating the M-shaped tunnel will cause some instability around this corner if we follow the shape. Eventually, we discussed with the JV and we proposed to have a larger excavation area just to allow them to advance the excavation as soon as possible, safely though. This gap here later will be backfilled by mass concrete. That's the idea. Now to carry out the design, basically we followed the same sequence. We use empirical method Q system, and we carry out 3D wedge stability analysis, as you can see here, and then we carry out 2D and 3D numerical modeling, as you can see here, and we include all the rock joints in the model, and we predict the ground movement and the mobilization of the support system. This picture here shows the pillar area of the bifurcation cavern, and this model was to predict the stability of the pillar because the pillar was quite thin, it's about 1 meter, and because of elevated stress during excavation, it may be unstable. Now for excavation design, to allow the JV to advance according to the program, we allow them to, or probably I should say, we design the excavation sequence such that they can excavate half face of the cavern. So the whole face is about 400 square meters. If we are talking about half face here, this area here is about 200 square meters. It's quite a big face. We need to carry out many assessment and analysis to ensure that there's no unstable wedge and instability when we excavate this area. And we have a robust support, long dowels or rock bolts. We have 8-meter rock bolts here and the 4-meter rock bolts here with shotcrete as well. And after they come through to the other end, then JV can come back to excavate the other face. I have a video I want to show you. Of course, this is the sequence taken from the video, but I hope I can share the video for a better view. Sorry, let me share another screen. If you have any problem, please let me know. So this is the excavation sequence. First we excavate the first tunnel, and then we continue with half face. We advance further.
Ivan, I don't think it's, I can't see it on my screen.
You can't see it.
Might need to just let it load for a second.
Okay. Do you think it's coming now?
Not yet.
Okay, probably I share my whole screen.
I can see that you're on it, but I can't. Here we go. It's up now.
Right. Sorry about it. So yeah, I will repeat it again. So we first excavate the first tunnel and install all the rock bolts, and here we go. That's the half face excavation. We continue further, and then we will come back to excavate the rest of the caverns. These are the third tunnel. These are the cross passages. Okay, so that's a sequence for the cavern though. Now, are you seeing my PowerPoint now?
Yep, back now. Yep.
Right. So again, similar concept. We install and we design and install a monitoring system across the area because it's a big opening there. And generally, the movement is negligible. What we record was less than 1 millimeter. And this is the layout plan of the monitoring arrays. Now I just want to show some site conditions during the excavation. This is a picture during excavation below the MTR tunnels. You can see the foreman there, and this is the drilling jumbo. So the jumbo helps us to install rock bolts, blast holes, drilling prop holes as well. And they are, if you see the little dots there, they are blast holes essentially. And you can see like the jointing of the rock, and the color difference here shows there is a weathering. That means there's a fault there. And this is the cross passages just below the MTR tunnel. Again, this is the jumbo, and this is the foreman, and they are drilling the blast holes. I think they are working on two phases, one here and another one there. This is the halfway excavation of the bifurcation cavern. Yeah, you can see it's pretty high, 14-meter high from the crown to the infert. Now this is the finished excavation of the cavern. And you can see this truck is, I can't remember the Caterpillar number, but it's about 6 meters long, and probably we can park more trucks here. It's pretty big. And this is the stage where they install the waterproofing membrane before they cast the permanent tunnel lining, concrete lining, in fact. And this is the picture of Flumping Portal. If you remember, we had a clear picture, but here is quite messy. The light blue color shows the location of the fire duct construction here and there. And there's a retaining wall construction in progress in this green area. And there's another tunnel excavation here just inside the slope. And these two tunnels are the one that I mentioned earlier. We excavated below the MTR tunnels there. And this is the view of the other portal, this Tseung Kwan portal. This is 31 meter high, 25 meter wide tunnel cavern, I would say. And these two openings will be connected to a sea bridge to another site. Just before closing, I just want to give a potential consideration for further, future design in terms of rock cavern support design and other rock engineering problem. We see that many people use empirical method a lot in rock support design. However, we need to be very careful how they were derived, because sometimes people just look at the numbers and they don't look at the boreholes. And we can see here on the right-hand side, this is a core box taken from a borehole, and there are some rock quality designation number here. And what we see, if the rock quality designation number is low, that means we are having a crushed rock. But in fact, you can see the rock is pretty massive there. So sometimes this happens, and sometimes we need to pay more attention to this, because it can cause, in fact, this is from experience, if we just forget about the core box or the fact, then we may end up with a costly design. It happens in one of the region in Southeast Asia, and in fact, when we investigate further, we can come up with more cost-effective design. And at that time, there was a tender, and we won the job. Now, modeling, advanced numerical modeling. Yeah, these days these are used a lot. For rock, I think we should be cautious as well, because rock behavior is not like soil. It's a bit different because it's influenced by discontinuities or fractures or joints, and also the fabric is unique. It's also influenced by in situ stress or tectonic stress. So it's an isotropic condition, And you can see on the left-hand side, this is a continuum model of rock tunnel excavation. Now, continuum model is like the ground strength here is an average of rock strength, so it includes the jointing factors and other considerations. So this is a continuum situation. We can see there's an upheave here, but if we compare to this continuum model, actually we see another problem here. It's not an upheave, but this crown beam is failing down. So sometimes we need to be very careful when we carry out numerical modeling. We need to really consider what is the likelihood of instability, because we cannot just take if you just rely on numbers, then it will be quite dangerous. And often we see, especially recently, we see that numerical modeling is often used, and people just plug in the numbers, and then we can come up with some results, but we need to investigate further. Another way to model rock condition, we can use so-called discrete fraction network approach. Essentially, discrete fraction network approach is another way to model rock mass condition to include rock joints explicitly in the model. Now, what we see on the pictures here, we have photogrammetry results with rock joints, and then we can put all the joints explicitly in the model, and then we can quantify many things: block size, stress length, and many other things. And then after that, we can try to bring it to a more realistic modeling. We can use discrete element modeling, for example. In discrete element modeling, we model joints as is explicitly, so we can understand the potential instability because of the jointing. Yeah, I think I hope that's useful. I'm not sure if Phil wants to add something. Otherwise, I look forward to questions. Thank you. Terima kasih.
Thanks, Ivan. Thank you very much for that presentation. It was absolutely excellent. Brought back a lot of memories for me. Some happy, some not so. But no, it was great, and I was glad you were in our team. Very successful project, and the risks we faced were handled very well. Yeah. So we have some time. I thought we might allow 10 or 15 minutes for questions. Does anybody, it would be nice to hear some voices. So does anybody have a spoken question first, that whilst we've got Ivan here, and then we'll have a look to see if there's any written ones.
Yeah.
We have silence.
Mm-hmm.
Well, I'm going to ask one anyway, Ivan. How many years of experience had you had before you led the design of that tunnel?
If I remember correctly, it was about seven to 8 years. Yeah, okay. Something around here.
Which part did you enjoy the most of the whole thing?
Well, I think I like ground engineering, so I like to understand the ground condition, rock condition, and further than that, I like, we understand the ground and we understand our clients, what they want, and we provide some solutions, especially when we, the excavation beneath the MTR tunnels. It was very challenging, and it was very interesting as well, because a lot of interactions with clients, MTR, tunnel team. It was very interactive, and I think it's really, really good experience at that time. And yeah, having worked with people from different backgrounds, it's really, I think we can come up with fruitful results.
Yep. So I've got some questions coming up. Mike, I think you'll be a spoken.
Once I found out, have I unmuted myself?
Yep, I can hear you, yes.
Well, Ivan, that was an incredible presentation. I'm a geotechnical engineer, so it's really fascinating to see that. I'm absolutely amazed by the level of detail of the jointing. I mean, how accurate was that level of detail, or was it based on general knowledge of joint patterns from rock cores and things, or every joint in that model was put in kind of accurately one by one?
Of course, if say we are having a plan for tunnel excavation, of course we never know what is the jointing look like later on. So what we can come up, and that is the key from DFN or discrete fracture network approach, is we can analyze the jointing from boreholes like Califia survey, and then we can try to quantify statistically, and then we can run some stochastic analysis to run probably 50 scenarios or 100 scenarios that potentially happens because of this pattern, something like that. So it's a prediction, and we, again, in rock engineering, I think we can, or we should, verify on site. But I can see that the DFN approach is, it's been implemented in oil and gas because they do a lot of hydrofracturing and they need to hit the right fracture, in fact. So it's been used for decades, and it's just in civil, it's not widely used. And we can see there are a lot of potential that we can gain from putting all the joints. It's not an exact representation of the site, but it's a probability assessment, I would say. Yeah. Okay,
no, thanks, very interesting. Thanks very much.
Thank you.
Next one we have, apologies if I pronounce this incorrectly, Ji Yu Young.
Yeah, hi, sorry. I think I have the same question as the Mike.
Okay. Would you like to ask it, or has that answered it? Okay, John Mundy.
Can you hear me?
I can, yes.
Oh, right. Excellent presentation, very interesting.
Thank you.
I was involved in Tseung Tunnel and Thailand Tunnel. And one of the things I was just wondering, was this project part of this overall plan to construct a tunnel which went right from Tseung Kwan right to West Kowloon? I seem to remember that this was, if you like, the first stage.
Yeah, I think this is part of the East-West strategic connection. So
that's right.
Yes. In fact, I live on the east side of Kowloon, and we have a beautiful view of a bridge, and that bridge is connected to the Tseung Kwan caverns, and then we will. I think it is connected to another project called T2 Trang Road. It's just another extension, and then it will be connected to. Now we have Central Kowloon Road project, and it will eventually, from Tseung Kwan area, we can travel to Yau Ma Tei directly without any,
Yeah. I was amused at the cross section. I saw your overhead vent ducts were the precast slabs, the sort of the arch design. This is what we did on the Tseung Tunnel. So obviously somebody else has taken up the idea. Anyway, nice presentation. Very good.
Thank you very much. Appreciate it.
Chen Sheng. Can you allow Chen to speak, Maria?
Yes, I'm already allow Chen Seng to talk.
Okay. Chen, you've got your hand up. Go ahead if you've got a question. Can't hear you, Chen, if you're asking a question, but maybe you need to unmute yourself. All right. Okay. I can't see any more raised hands. I don't see any written questions. Oh, hang on, one more coming through. Eng Fin, you have a question.
Hi, can you hear me?
And welcome back as well.
Thank you. Yeah, so I'm a structural engineer working in Hong Kong as well. I don't really know much about like rock or tunnel engineering, but I would like to know, like from your experience, is there anything you think is very unique in Hong Kong in terms of designing or like delivering a project? And maybe you have a story you want to share.
Very unique. Well, the unique thing here is everything is about queue system. I think that's the unique thing. And I mean, it's been used in many decades, and I think well, hopefully this doesn't sound too negative, but sometimes I feel rock mechanics is forgotten in you know, rock tunnel design, because people just get used to you know, queue system. It's quite easy to just plug in the numbers and we can come with a certain you know, support solution. But if we move out of Hong Kong, the rock can be different. For example, in Sydney, the rock is not like Hong Kong. It's not granite. It's sandstone. It's horizontally based, and they have high institute stress condition. And the problem is not about wedge, but it's about brittle failure, spalling. So you have like sort of crushing, and it happens in concrete as well. And similarly, in for example, Eastern Canada, they have the same problem, and that also happens in deep mines. So when people they have experience in queue system, and then they think that it can be done in any you know, rock conditions, we need to be a bit careful, because queue is probably not just queue, but like queue system or RMR. They were built for based on certain assumptions and certain data sets, and it was based on certain geological conditions. So sometimes we need to go back to you know, like geological conditions to look at the boreholes and then outcrop, and then we need to check whether there is any other potential instability that we may miss, something like that. And it goes the same way for numerical modeling. You know, Pluxis or other finite element modeling is very popular right now, and people can just, you know, plug in a number. But if, for example, we use Hook-Brown method for massive rock, in fact, it's not right, and it's been emphasized by Hook and Brown themselves. They are not built for massive rock condition. It's built for heavily jointed rock. And again, if we talk about whole area, we need to be a bit careful again if we want to use, like, for example, Hook-Brown method, and it is not applied as well. And we need to you know, we need to have different assessment. So I think in rock tunnels or rock engineering projects, they are not as straightforward as the typical design, I would say.
Is it due to like the culture or the requirement from the government that the people always refer to one method and not really open to another method?
I can see Phil is smiling there. Yeah. I can agree to that. Yes. Personally, I can feel that Hong Kong has probably, you know, about GEO or BD. They have heavy, you know, procedures and regulation, and all needs to be approved by them. Even new materials, even, you know, like new rock bolts or new instrumentation system, they need to approve it. And yeah, sometimes it's limiting understanding, I think. I'm not sure, Phil, probably you want to add to that.
Yeah, it's the regulatory processes in Hong Kong are extreme, and for good reason. You know, this was a serious project, and damage to the MTR lines could have been catastrophic. Sometimes you feel it's taken a bit too far. Sometimes we felt like we had 5 or 6 clients. We had our contractor, we had the owner's engineer, we had the owner, we had GEO, we had the buildings department. And, you know, you feel that you're jumping through a lot of hoops. So, yeah, I'm not saying that's wrong. It's just, at times it can slow innovation because it's difficult to get new ideas through because nobody wants to or likes to take, who likes to be first. And this is a problem with, you know, innovative ideas. Ivan touched on some advanced modeling that we looked at towards the end there. It will take time to get those kind of ideas through the regulatory processes. And sometimes when time is money, it's not always possible to do that. So yeah, it's got its frustrations, but when you're tunneling underneath a large city, the consequences are very high. So yeah, I can see where it comes from.
Yeah, just like, because in my field in structural engineering, we also kind of face similar problems. So sometimes we have to do like more advanced modeling with some softwares, but then they have this list of software which are accepted, and you can't submit anything without that like pre-approved software kind of thing. So
well, you can get your software approved, but you have to go through a process beforehand. So don't give up.
Yeah,
do try, because you'll get there, but you've got to be prepared to work through it. Mike, you've still got your hand up. I don't know if you've got a question or whether it's still up from before.
No, actually, it was just a supplementary one. I mean, first of all, just an observation on the GEO. I mean, I've been going backwards and forwards to that office for many, many years, and I thoroughly appreciate the background to the things you're talking about. If no one else had experience of GEO, it's a fairly unique experience. And but I just know I had another question which struck my mind right from the beginning, was that I don't know how many blasts went off during the entire construction process. It must have been thousands of them. I'm just wondering if there were people could feel this in that area and started to complain about it or got upset about it. I mean, you can just imagine little bumps going on every now and then, and it disturbing people. So I'm just wondering, the level of vibration, whether it could be detected by humans.
During the excavation it was very controlled. In fact, when we excavated under high-rise buildings and MTR, we reduced the MIC, the maximum instantaneous charge rate. So before we were not the blasting designer. There was another consultant helping the JV to carry out blasting assessment before excavation. So they first plan which one is high risk area, and then they would come up with certain MIC numbers. But during the excavation, there's no complaint from stakeholders. Or I just remember there was one time, I think the JV missed the window, the blasting window, during excavation beneath the metro tunnels, and that's it. It was, it was very limited, 2 minutes, and if you miss anything, then you need to wait for another day. But yeah, in terms of vibration, it was very controlled.
Oh, thanks very much. Interesting, really interesting to listen to that. So thanks again for all your effort to present that to us tonight.
Thank you, appreciate it.
Okay, guys, I can't see any more hands up. So if anybody thinks of a question later on or whatever, please feel free to email us at the ICE and I can pass it on to Ivan. Thank you very much, Ivan. It's great to see you around again, and thank you for reminding me of all the fun we had together.
Yeah.
Thank you very much again. And before I hand back to James, thank you from me to all the people that attended. Enjoy your evening, and I'll give the controls back to James.
Thank you, Phil Mansey, for your kind remarks, and also to the speaker. Once again, thank you, Ivan Haryono, for your excellent presentation, and thank you also to Phil Mansey for guiding the session. Ladies and gentlemen, we have now reached the end of the event, and for information, you can access your e-certificate through the link s.id/ICE3June. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone.